folks still trying to come in. Wow, what an audience. This is incredible. I was just glancing around at you guys, and it's like David Phillips, Matt Patrick, John Dvorak, Frank Trusdell. If a lightning bolt strikes this building, that's part of the volcanologist for the Western Hemisphere. That's right here. So, woo, what an incredible night. Just love it. So, do I have any other housekeeping, George, or is that everybody scoots towards the middle? Oh, Frank has also brought some wonderful handouts. The best of Michael Bublé. No, I'm kidding. It's CDs with all kinds of cool images on there. And he's also got a poster that would be great if any of you are teachers or educators. Really, really good option for you. And it's free, so very cool. All right, so what do we got going tonight? It is the last evening for the After Dark in the Parks for Volcano Awareness Month. And we might as well end on a really high note, which is what tonight's in. And we have two speakers tonight. Our first speaker is Ingrid Johanson. She's a research geophysicist at Hawaiian Volcano Observatory. She grew up, and I got this mostly on the online research, so if I get anything wrong, correct me. She grew up in California's Central Valley, just east of San Francisco. She is no stranger to earthquakes. It was the summer internship in geophysics that inspired her to study earthquakes. At the time, she was a UCLA undergraduate pursuing a degree in physics. And through the internship, she discovered that geophysics would combine her love of math and physics along with her appreciation of nature. As part of her subsequent graduate research at the University of California in Berkeley, she helped develop a technique using GPS and satellite radar data, that's INSAR, right, to map surface motion. Her work led to new insights into how stress accumulation occurs along faults, including the famous San Andreas fault. So it relates to the potential for future damaging earthquakes. After her PhD, she held a prestigious postdoctorate fellowship with USGS, where her research results have been incorporated into, are you ready? California's earthquake early warning system, because of the work she's done. Is that incredible? In 2015, she brought her combination of GPS and INSAR expertise to HVO, where it has had great potential to further our understanding of volcanic and earthquake processes here in Hawaii. And I think I've got a ranger that's got a nice sleigh for you. Ranger Roger, come on up and there you go. So Roger's one of our volunteer rangers, and I said, could you put the lay on for... So I asked Roger, could you put the lay on for Ingrid? And he said, yeah, is there a ceremony? Yes, there is. There's a dance involved. It didn't work. Yeah, he knew. He was like, oh, it's Dean. No, there's no dance involved. Our other speaker tonight is Frank Trusdell, a research geologist at USGS's Geological Survey, Hawaiian Volcano Observatory. He was born on Oahu. After graduating from Kamehameha High School, he earned a Bachelor of Science degree from the University of Hawaii in Hilo. Then he went on to attend University of Hawaii at Manoa, where he received a Master of Science degree from the Geology and Geophysics Department in 1991. His work has included a wide range of field-based studies and the production of detailed geologic maps of Mauna Loa, the largest active volcano on Earth. He also led the effort to create and publish lava inundation zone maps for Mauna Loa. Those maps provided information that have helped emergency managers identify people, property, and facilities at risk during future Mauna Loa eruptions. Okay, that would be a good pedigree if I stopped there, but in 2022, Frank received a Meritorious Service Award. That is the second highest honorary award that can be granted to a career employee by the U.S. Department of the Interior. Wow. Unbelievable. In the citation, they said his meticulous investigations of eruption histories, his calm demeanor, his decades of experience have critically informed HVO hazard assessments shared with the public and emergency managers. After 40 plus years in this career, he was asked about his highlights with HVO, and he replied very simply, working with great people, monitoring eruptions, mapping Mauna Loa, and mentoring up-and-coming volcanologists. Yeah. But that's the
Okay. As we were introduced, it's going to be a program where Ingrid and myself will be a tag team. And Ingrid will be presenting the geophysics side, and I'll be presenting the geology side. And I'm going to say that if you read this little note down here, that I've shamelessly taken materials from my colleagues. So just consider this an HVO-wide presentation as opposed to Frank and Ingrid. Okay, so let's look at the geologic context of Mauna Loa volcano. It's the largest active volcano on Earth. It's a high threat volcano as identified by the USGS Volcano Hazards Program. Comprises 51% of the surface area of the island of Hawaii, which means that even though you don't live on Mauna Loa, because the lava flows can impact the island, whether it's to the northwest, the west, Hilo, it has far-ranging impacts that impacts everybody on the island. Just imagine it cutting the highway, as was a potential in 2022. The previous eruption to 2022 was in 1984, and I actually was here as a junior person to work on that eruption, and it was fantastic. Okay, looking at the pre-eruption, in September of 2022, the seismicity increased. And so we felt at that time, it seemed like Mauna Loa was reawakening. And so we took our show on the road to try and go out and inform the communities around the island about the potential impending eruption of Mauna Loa. And the place that we focused on was down here in the southwest side of the island. And the reason why we focused there is if you look at this map, what we're looking at is transit times from when vents opened on the flanks high on the mountain and lava flows cascaded down into the ocean. So we're talking 3 hours, 14 hours, 18 hours. And we wanted these people to be aware that Mauna Loa could possibly reawaken. And because they had short response time, we wanted them to actually prepare. So that's where we focused our energy initially. And this picture just shows us out there in outreach, reaching out to the individuals. And my personal mantra, not the USGS mantra, for talking to these people down there was, if you see the glow, it's time to go. Okay, the events leading to the eruption. And this is Ingrid.
All right. So for the purposes of this talk, I'm going to start in 2002. But as Frank said, Mauna Loa has a long history. And so even the deformation, the geophysics, it's really hard to pick a starting point. But one of the reasons I'm going to pick this starting point is it's coming in right before one of the first real pulses of deformation post-1984 that we detected. And it was detected using a relatively new tool, which is GPS, the Global Positioning System. So this bottom panel down here goes from about 2002 up until right before the earthquake. And what you're looking at is the difference in line length between two GPS stations, one up here at the summit, and then the other about halfway down the flank on the east side. And so as the volcano inflates, the length between these two sites gets longer, and you see this distance increase. So here in 2004, 2005, we saw this first big pulse of inflationary motion. It did eventually calm down. The alert level was put to yellow during this time period, but then it was brought back down to green. And we did reach what could really be considered background again after that pulse. But then in 2014, it started up again. And in 2014, there was a little bit of a difference, and that had to do with the seismicity. So the top panel here, this is the earthquake occurrence. So this is a histogram showing the number of earthquakes per month, also from 2002 until present. And during the inflation period here in the mid-2000s, it looks like a modest pulse of earthquakes. In fact, there were quite a few deeper earthquakes, but it was definitely a different pattern than what started up in 2014. In 2014, we started to see shallow earthquakes starting to occur around the summit area. And once things started in 2014, they never really went back to zero inflation. Sorry, let me go back. So starting here in 2014, this was when we really started talking about hazard with the community, Mauna Loa hazard in particular, because of these two signs changing together. And again, the color code was changed to yellow. There was a nice period where things really calmed down a little bit, and it was lucky because that was during 2018. They let us respond. Mauna Loa let us respond to Kīlauea before really starting up again. So you have this long period of 10 years, and you start looking within that 10 years of when you should start to escalate your concern even further. And one of the signs we were really looking for was that evidence that the magma was getting even shallower. So here we see it starting to inflate. Now where is the magma going? And one of the lines of evidence that magma was in fact starting to shallow in, I've lost the laser pointer. But and that's not very visible at all. Let's see if I can make that better. Maybe that's doable. So here in 2021, one of the signs that activity was getting shallower was when we started to see clear signal on Mauna Loa's network of tilt meters. Tilt meters are in particular very sensitive to shallow changes in inflation. So they're more sensitive to shallow than GPS is. Those of you who look at Kīlauea's tilt meters are probably familiar with seeing those respond all the time to what's going on at the volcano. The big difference between Mauna Loa and Kīlauea was the depth of the magma chamber. The shallow Halemaumau chamber is at about a 1 kilometer depth. It's very shallow. So this was kind of a sign that things were coming into the depth range that we almost think of like Kīlauea. So like everything was starting to get shallower. So this was the first sign. This is I say contraction because it's actually still a very intriguing event. I can't say I totally know what happened during this time period, but there was a decrease in line length across the summit, an increase in earthquakes, and then tilt that's usually in the deflationary direction, so inward tilt. It all happened together. All of these happening together really put the nail that this was a true volcanic signal in the tilt meter and not something else. So this was a really important sign that we should be on the watch for shallowing. Another way to watch for shallowing is through computer modeling. And the wealth of GPS data that we have here on the island at Mauna Loa really helped with that. And I do have that mid-aughts inflation event to thank for the GPS network, because it was that impulse of inflation that really led people to prioritize instrumenting Mauna Loa such that it could be monitored in the way it was able to be monitored in the lead up to this eruption. So in a couple slides, I'm going to present a model of opening, the inflationary opening of this tabular body through time. But just to set the stage a little bit, the basis for the geometry I'm using is 25 continuous GPS stations. So each of these arrows around Mauna Loa is a GPS station. The direction is the direction that spot is going, and the length is the speed, that's the velocity. This is going from, I believe, 2015 to 2017. So in addition to these 25 continuous stations, we also have 37 campaign GPS stations. And what this is, these are brass benchmarks in the ground. We go with a tripod and a portable antenna, and we set up for 3-4 days over the benchmark to get a yearly position. So we don't have the time information of a permanent continuous station, but we add in density, and that really helps pin down this geometry. So ultimately, the geometry, you can see there's a line here. This is representing a dike-like tabular body, so almost like a wall of magma in the volcano. There's also a point source, which is really just a stand-in for some sort of equidimensional, slightly spherical source. And then this bigger rectangle is a décollement fault, not unlike the décollement fault underneath Kīlauea. So this is a sliding surface between the volcanic pile and the original oceanic crust. And because I'm modeling years of data, it is important to keep that, that contributes as well. And that's the model fit, so be impressed by how well it fits. But so for the model I'm going to show, so now we're looking into the volcano. So this is as if we were standing at Kīlauea. You're looking into Mauna Loa. This dashed line is sea level. This here is the ground surface. Mokuʻāweoweo goes from about there to there. And then the pit craters that make up the southern summit region are through here. Let me see. I think I'm gonna leave the reading to the interested people and then move along to the movie. So this is starting in 2014. So here's that viewpoint. This is smoothed in space and time. So you'll notice it's very smooth. So the warm color indicates opening rate. So if it stays a steady color, it actually means it's continuing to open. As the color disappears, it's not closing. As the color disappears, it just means it's no longer opening. This was an interesting shift into this southern summit region that happened in 2016. It was actually that shift into that southern summit that inspired really working this model back up again, because it was clear we couldn't use something static to monitor it. Over here, so this line here is the volume in the dike. This line here, I think it's supposed to be red. I don't know if that's coming across, but that's the volume in the point source. And then there's a slip rate here on the décollement fault. So now we're in that green pause, and it's about to start coming back up again. And at first it started, so here we are under Mokuʻāweoweo. After 2018, it started up first with this sort of mid-crustal reinflation. Oh, the black dots are earthquakes, in case that wasn't clear. So earthquakes that are happening simultaneously. And then we started to see this really deep opening. And this deep opening would persist, and in fact would start to march up and up and up and up. And remember, the colors are opening rate. So even if it stays red, it means it's just continuing to open more and more. And as this started to push up, we started to see fingers going up. These two fingers correlated with very clear increases in seismicity. So where this was very steady, these seemed very clearly associated with increases in shallow earthquakes. And in particular, this one happened together with an increase in seismicity in September of 2022. And it was that increase in seismicity, which did not go down, it persisted until the eruption, as well as seeing this very clear evidence for everything getting shallower that really put our antennas out that, you know, it's really getting closer. And I think it's you now.
Okay, so this is a thermal camera and the summit, and it's looking out there, and the temperature bars are here. We're looking across Mokuʻāweoweo. This is to the southwest, and this is to the northeast to the left. And the fissure then cut from that southwestern part. Right here, you can see an increase in temperature that actually preceded the geophysical signatures by 2 minutes before the onset of the eruption. And the lava then migrated across the caldera there. And as the dikes opened up, we started to see that social media started to blow up because people in Kona started to send pictures. This is down here at Kīlauea, Kona, and they're looking up and they see these fingers of lava coming, and everybody was all pretty much totally thinking that lava was descending upon where they live. And the case is that there have been other eruptions in these time periods shown here in the bottom that lava has been visible in this area. This is an area that's part of the South Caldera. The lava is cut across a high plateau. They are visible. There have been no eruptions in the historical period where lavas in this area have ever threatened where people live. So this is normal, even though people were quite, let's say, worried. Okay, so early in the morning after the eruption opened up, we got on the first flight, we flew up to the summit. You can see that our camera at 6:11 shows that there's still lava in the caldera. By the time we arrived 20 minutes later, that's what it looked like. It was already, all the fissures had shut off and we couldn't see any incandescence in this area. We flew over to the South Caldera area to look for active fissures, as people were reporting the night before from Kona, and all of these in turn were also dead. And we couldn't find any incandescence, although we saw a lot of degassing. So you're looking up the Southwest Rift Zone, there's Mokuʻāweoweo. And then from there, we moved over to the Northeast Rift Zone. Looking at our webcams, we saw the earliest glow that I could identify, that I felt confident of something intruding into the Northeast Rift Zone, was about 0548. And then the fissures then opened up as in discrete members. By the time we got there, we saw 3 sets of fissures, and we saw the 4th one open up.
All right, and I'm going to rewind in time a little bit to talk about the same events, but with a geophysical angle. So now I'm rewinding us back until just before the eruption. And what you're looking at here is something called a spectrogram. So there are 6 instruments, 6 seismometers represented here. Each stripe is a seismometer. And within each stripe, at the bottom is the representation of the lowest frequencies, and at the top is the representation of the highest frequencies. So if you think of it like sound, all the low notes are down here, and the high notes, the high pitch is up at the top. And then the color goes with how strong that is. So strong, low things at the bottom, strong, high things at the top. This is generally how our seismologists look at seismograms these days. They don't look at wiggles anymore. So we're constantly told we should be looking, us other geophysicists, we should be looking at them this way. The thing to take away here is the prior to, this is 1124, this seismogram here, all of these through-going stripes are indicating earthquakes. So when an earthquake happens, you see this very clear pattern. This was normal, and then starting at normal for a volcano in unrest, so not normal. But as usual, I guess I should say. And then at 11:24, earthquakes started coming fast, fast, fast. And it was barely an hour later when the eruption onset happened. And within the geophysics, you can see that here. So you have these nice stripes, these enhanced low frequency events. So you've got these nice earthquakes, and then you move into fuzz. And the fuzz is when you've entered eruptive tremor. So things are just going all the time. And that's very typical of once the lava is fountaining and pummeling the ground, you end up with, and you've got bubbly material moving through fissures, you end up in this no longer nice, discrete earthquakes, but eruptive tremor. So 10 years of warning, and then also 1 hour of warning. So all depending on like how you look at things, it's either a lot or not very much at all. So on the deformation side, the instrument that we look at on this type of time scale is our tilt meters. And so this top panel here is the tilt meter I was showing earlier. It's up here near Mauna Loa summit. So this is spanning several hours on the day of the eruption. So as the earthquake started, so this line here shows when there was these intense earthquakes, and we didn't really see much in the way of deformation until there was one biggish earthquake that seemed to really unlock the system. And so it waffled around for a little bit, but then at about 11 o'clock, we saw this clear increase in inflationary tilt. So these two lines are at right angles to each other, but nonetheless indicate, they give us some idea of what direction it's coming from. So this direction was indicating something was opening, a fissure was opening. And then eruption onset, we had a tiny bit more opening, but then pretty much turned right around. And this initial increase, which is the fissure opening, was happening very shallow. But then once you turn around, generally that's a much deeper signal. So it's hard to tell with one instrument, just a tilt meter. But it did not take long after material started coming out onto the surface to switch from this fissure opening mode to deflation as the magma chamber started losing material. This bottom panel here is a tilt meter out here in the South Caldera area. So this tilt meter, we still haven't gotten a chance to go visit it. We've actually been trying very recently, but the high winds at Mauna Loa have stopped us. So I'm not actually sure its condition. You can see that it's right in these mapped fissure traces. And in fact, the eruptive fissure that came to the South Caldera came very close to where it's mapped. And I'll be very curious to see if in fact it got, how it might have gotten affected. So the MOK tilt meter was this first one that was very clear. And then as the hours went by, SLC started to really get going. And then, this is going even more hours. This is going out until about 9 or 10 a.m. So MOK was doing a nice deflationary pattern, whereas SLC was ramping up and then eventually went off scale. So that's essentially, that's the limit of those tilt meters. So definitely had our eye on that South Caldera. The direction of motion was not consistent with anything moving towards, downwards down the Southwest Rift. The direction of motion did seem like whatever was happening to the west of that instrument. But ultimately, this was the instrument that showed the highest amount of deformation, not the one that was right at the summit. But it may be because it was unfairly very close. So this is a very preliminary model. I don't have the same run-up as the other one, but it's following the same basics. But so this now, instead of being, going over several years, this is going over about 2 days. And so this is using the GPS data at a much shorter time spacing than we usually do. And so there's a couple things. This is, like I say, it's very preliminary. You'll notice that here's the ground surface. It goes off into the air. That's not usually something you want from your model. So these are all things that are going to have to get changed in the future. But I'm really excited about it, so I did want to show it. It goes by really fast, but then I'll go backwards, I think. Oh, there we go. Ooh, there it goes again. So what's happening here? Uh-oh. So what's happening here is we're in the run-up to the eruption. Eagle-eyed people will notice that things happen before they're supposed to. And that is also because it's a preliminary model. I've got smoothing in time going forwards and backwards. I think as I do better, I think I can smooth only in one direction so that I can preserve the timing. So if this means anything to you, this model is currently acausal. I'd like to turn it into a causal model. This is, so don't pay too close attention to the time that's in the corner, but this is the timestamp of the model. As we get started, we see that very clear, here's Mokuʻāweoweo. So this is that very clear fissure opening right underneath where the eruption occurred. And then when we step through, we see it sort of move into 2 pieces, and one heads off to the southwest, and the other heads down to the northeast. And that's maybe not. So now we're in this situation here. This is maybe feeding into that southern summit fissure that erupted for a little while, whereas this sort of blob, this fissure, this is indicating opening of the rift, which then allowed the eventual eruptive fissures to open and become the sources. So again, I was able to do this with just our existing continuous network. It wasn't required to scramble stations in order to do something like this, which is partly a testament to the network that was put in before I arrived at HVO. And yeah, that's the. I'll play it at full speed one more time. It goes by very quickly. Oop, and that's you.
Okay, so now we have fissures opened up on the northeast rift zone, and the geologists go out and start to gather the data. So we went out and we did some lava flow sampling. We had a UAS also out there looking at channels over time to look at velocities and the morphology. We had thermal images, airborne mapping, and not only did we watch flow field development, we also looked at channel development and also monitored the flow front, because the flow front possibly could impact the saddle road. We also set up these web cameras, and those of you later on during the eruption noted that we also had a real-time camera out there where people could go and stream that and look at the streaming data. And when we use cameras like this to look at eruption dynamics and see fountain heights and how that relates to the seismicity and the flux, how much lava is coming out at time. And when the weather wasn't so good, we also had a secondary way of keeping track of the flow field and how it advanced, because sometimes the weather wasn't great. So one of the things that we do with the lava samples is that we go out and we look at the chemistry, and the chemistry can give us ideas about the source of the magma, how long the magma has been stored, whether or not that magma is a mixed magma. We can calculate the temperature. And those are some of the things that we can do with the lava chemistry. So here we are, we're collecting a sample of lava and then we quench it. So we take those quenched samples and we make a series of chemical plots. We use, in this case, we're using calcium oxide and magnesium oxide as a proxy for the lava, what we're looking at, and this is their concentrations. And you can see that over the course of the eruption, these yellow dots represent all the samples that we collected. So it's spatially well defined, and we got stuff that goes down the flow field. And the surprising thing is it's uniform. Right? This is time over here, and you look at the chemistry, it's uniform. And we thought, well, you know, after 38 years, we would hope that we would see something different, especially with different pulses that we tracked that Ingrid talked about. And yet it was surprisingly uniform. Now, we also was able to take some of this data and do it in near real time in Hilo. And then we could look at the sampling, because that might inform us if the temperature is going up, maybe the lava is more fluid. And therefore the flow front would advance more quickly towards the saddle road. But then we also were able to do physical parameters on the lava, and you can use that to put that into lava flow models. Okay, so the chemistry itself was fairly, I don't want to use the word boring, but unremarkable. How's that? It was unremarkable, except when we started to dig deeper, we took a trash can sized barrel of cinder and we crushed that all the way down to sand-sized grains looking for olivine, because when we got the samples and we look at hand specimen, we saw no minerals. Then you take that tephra and you crushed it all and you got olivine grains like this, and you can see they're small, about 1 millimeter. And these actually tell an entirely different story. So these olivines right here are very primitive. The lava that we collected, the whole rock analyses, is indicative of lava that's been stored for the 38 some odd years. And these lavas say, no, this is a very juvenile thing that came. And when we calculate, we look at the inclusion data, we can actually get a pressure calculation from these olivine, and they can tell us different areas within the subsurface that they equilibrated with. So we're looking at very shallow storage, like Ingrid said, and then we go down to these areas as far down as 5 kilometers. And we're looking at the seismic data over here to inform us where the magma chambers might be. And over here is a stylized cartoon of how these olivines that have these very deep signatures moved up in the system, re-equilibrated, and then finally were erupted. Now, some of these olivines spent very little time, and so what we're looking over here is duration of time. And we analyze the olivine. We actually look at their profiles from the core to the rim, and we look at diffusion models to calculate residence time. So this suggests that the bulk of the olivine were perturbed in the time frame about September, when we thought lava was stirring, that something was in the system, as Ingrid's models are suggestive of this. And that all is starting to unfold and link together how these things are overlapping for us to forecast an impending eruption. The other thing that was a novel thing that was broken out during this eruption is the fact that there was this lava 2D model. This model would use the physical parameters, the temperature, the vesicularity, the crystallinity, to then run down slope and calculate where the flow would be at a future point in time. So this model is projecting out for 2 weeks in time how far the lava would have advanced. And this model basically said that they would never reach the Saddle Road area because the flow was cooling more than it was advancing, and therefore it just kind of would freeze in place. Okay, how does this eruption compare to the 19th and 20th century flows for which people were here that actually documented eruptions. We're looking at the duration was 13 days for 2022. And if we look at other flows in this 20th, 19th, and 20th century, we're looking at flows that have median and mode values right in the ballpark of what happened in 2022. If we look at the area covered, we're basically in the ballpark. And if we look at the volumes, we're about 10, 12% of what those values were for that historical period. So what does that say? The 2022 flow was ordinary. Okay, taking a longer term perspective by using a geologic mapping, what did prehistoric lava flows tell us? Well, I've taken the Northeast Rift Zone and broke it down into segments. This is the upper, this is the middle, and this would be the lower. The fissure system right here, this red lava flow here is the 2022 lava flow. And we're looking at, this would be the mode, these great circles. This would be the average, and this would be the median values. The prehistoric lava flows told us exactly what the model told us. Very unlikely that that flow would have hit the Saddle Road. But I want to point out that you see this great circle out here? That is one of the outliers in the prehistoric period where lava flows can reach all the way down to Hilo. The frequency at which this happens is about one flow every 1,000 years. Okay, not to leave out some of our other colleagues who aren't here presenting with us, this is their gas data. We're looking at the gas in kilotons. So in 2018, there was about 200 kilotons per day. The Mauna Loa system, the fissure opens up, it starts about 200 kilotons. As the fissures propagate away from the summit, both sides of the Southwest Rift Zone, Northeast Rift Zone, that number goes up to about 500 kilotons. As the fissures die along the Northeast Rift Zone and Fissure 3 becomes a dominant source, it goes quasi-steady state and then dramatically drops off towards the end of the eruption, coincident with the RSAM values. So in this plot, we're looking at RSAM. So just think of seismic shaking. So the bigger the values here, we're looking at the more intense the shaking. So this is a sort of a pictograph of, here's the summit phase opens up, we have these fountains. Eventually, as both sides of the rift zone join the summit in activity, we have this big peak here. Fissure 3 takes over, we go quasi-steady state, and then the RSAM dropped off dramatically, and as the RSAM dropped, so did the lava production, and then eventually the eruption ended. So there were a lot of successes. We were able to call the start of the eruption. We went out early to message to the public to say that Mauna Loa was getting ready to erupt. We have great data set of things that we collected in the field. We had real-time data sharing with our partners, and there will be a journal that will feature a lot of people's independent research on what we found during the Mauna Loa eruption. And so there are more discoveries to come. And as I say, that the material presented here is not only mine, but a whole plethora of people at UHH, at the Hawaiian Volcano Observatory, and then, of course, we want to mahalo our partners. Okay, thank you.
I think you're still mic'd.
Ingrid will be happy to answer any questions.
Any questions? Yeah, right here.
There was a technique developed fairly recently to use the natural earthquakes of the Earth to model the
Yeah.
Would you use all of the earthquakes in this situation to do something?
Yeah, so the question was that there is so it's actually not such a new technique. But there is a technique to use earthquakes to then essentially, get at the structure under the earth. And the word for that is tomography, and it works a lot like a CAT scan. So you're using the energy that earthquakes send through the earth to then figure out what the density structure is. And the answer is yes, we could do that. There are some resolution issues with natural earthquakes, but as part of the recent the funding for post-2018 research, we just completed a large project. It's not natural earthquakes, but to use a truck that came and shook the ground for weeks here at Volcano. So that happened recently. It did require an array of over 1,000 little seismometers, so what we call little nodal seismometers. And that was, as far as I'm aware, the largest deployment of nodal seismometers that's happened yet. So we are excited to get the results of that, to get some of the structure of Kīlauea. That one was focused on Kīlauea from that. But yes, you can use natural earthquakes, although the resolution is not as good as sending out thousands of these portable seismometers. Yeah, in the back.
I have a question about this place. I never came of it. That was put up, and you haven't been able to get to it because of the wind. Did it go up in a windy place?
Oh. No. So it's the tilt mute that I'm talking about. So it's just, this is an item. So it's not that we haven't been able to get to it since the eruption, but rather once we finally worked through our priority list, we're now in this time where we've been having these really high summit winds. So it's at the winds that have kept us from getting there are just the typical high summit winds that have been happening recently. Yeah. Yeah, right here.
Do we have any idea when we'll be seeing an eruption again for Mauna Loa?
I'm gonna give that one to Frank. So the question in here is any idea when we'll see another eruption at Mauna Loa?
And the answer that I will give you is, as soon as you saw all that great geophysical data, as soon as that all starts to turn around and point in those directions, then we'll start forecasting. But right now, the volcano is showing that it's quieting, and so we have to just wait until the sensors show us something else.
In the same vein, what about Kīlauea? I know that you're doing reports every day. Are you seeing anything change? Because I was looking at I went to another talk, and they talked about where there was inflation happening more recently, recent eruptions. Are you seeing any indications right now?
You know what? This person right here was the duty scientist and can give you a synopsis of the last week's activity at Kīlauea.
Actually, I think it was Frank. Yeah. So the question was, well, could we give just a little summary about what's been happening recently at Kīlauea and where we've been seeing inflation? So I'm not sure how long ago it was exactly. It was not that long after the September eruption stopped that we began seeing both deformation and earthquake production in that southern caldera area. So just like Mauna Loa, Kīlauea's summit area actually reaches further south than the modern caldera. So it's this area just south of the modern caldera that we call the South Caldera. And so there have been periods where the earthquakes have sort of migrated even further south. And we have a very excellent GPS network on Kīlauea as well. And so we have been able to track some of that opening. At the moment, the deformation data is indicating inflation in shallow Hale Ma'u, which is the typical, usual underneath the modern caldera source, and a source that we sometimes call the South Caldera source. And that one's a little bit deeper and in that shifted space. So when we see these South Caldera earthquakes, that seems to correlate with an increase in inflation in that source as well. So it is an interesting change post-September. Pre-September, we did not see nearly as much action in that South Caldera source. A question right here.
I have two questions. The first one is, well, they're kind of the same way, but the first one we were talking about the maximum depth that we were able to get, which is 5 kilometers. So is it really the top portion, because the bottom that we technically get lava from? And my second part of the question is, the last eruption, we saw the lava flow within maybe 120 days. Is that really fast? How long did it be?
Okay. So the first question, so did you mean in my model that my model stopped?
No.
Or his, okay, yeah. So it's the olivines, I think. So wondering if 5 kilometers is the floor. So the question was that there was a depth of 5 kilometers. Is that the floor, the deepest you might source magma? And also, is 121 days of an eruption, is that, because that's kind of a long eruption. But
I believe it was the formation of the lava.
It was, one of the olivines had a diffusion time scale of 120 days.
Yeah.
So what it's showing you is that we have different populations, and the population is reflective of the different residence times. And so not all, because over time we have pulses of lava coming into the system, they have different diffusion scales, and it's saying that that lava, that material is reflective of something that happened 120 days prior.
Is that quick or?
I think that is that quick for equilibration, you mean, or in terms of a pulse of lava and then we sing the signature?
Pulse of lava.
I would say, that's a good question. Is that, I guess you would have to look at the scales. Okay, so let's go back and look at the deformation data. Let's start with, if you look at the deformation data and you see it in the shallow environment, the question is that the instance at which the lava is ascending into the volcano? Or is that the point at which you have sensitivity to actually record the lava moving into the volcano? And so it's sort of like a question, chicken and the egg thing. Okay, so going back to the olivine though, if you look at the olivine composition that we see in the core is reflective of olivine that's supplied from the mantle. So that's at the base of the volcanic pile about 14 kilometers below Mauna Loa. So the question you asked was whether or not 5 kilometers was where that lava originated from, and no, that lava ascends to, and it looks like at 5 kilometers depth is a possible storage area where that lava is sitting, and then there are other shallower storage areas, and they get interconnected with different activity levels.
Thank you.
Yeah.
oh, question right here.
A recent coffee talk with Bufi, we were told that there's some correlation, reverse correlation between eruption periods at Kīlauea and Mauna Loa. So we elaborate on that.
Yeah, so the question was that there is an idea that there's a reverse correlation between eruptions at Mauna Loa and Kīlauea. When one erupts, the other stops, and vice versa. And I guess, so I will venturing into my personal opinion, right? So I don't think that the data is I don't think the data is solid enough to say that there's no discussion as to what's going on. So there has been this observation A lot of it seems to have started in 1980 when Mauna Loa stopped having its eruptive phases and Pu'uo'o really took over. I want to live a couple hundred more years before I'm ready to say I really see that. What I will say is the volcanoes do talk to each other through their pressure systems. So when Mauna Loa goes through a strong deflation, it actually relieves a bunch of stress off of Kīlauea. And it means that Kīlauea suddenly has a lot more space to expand into. So there's definitely a mechanism to have some anti-correlation like that just through the pressure transfer between the two volcanoes. Where I get hung up is on the why, beyond just the observation, I guess. But Frank has some.
Okay, so my perspective as a geologic mapper who can look into several thousand years of eruptive history is they're anti-correlated. So when Kīlauea seems to be really active, effusive, meaning lava flows and the like, then Mauna Loa appears to be not dead, but quieter. And then when Kīlauea moves out of that phase, Mauna Loa seems to have lots of eruptions. And we can show that back to 0, like as in BC, AD. We can go back that far and show.
Don't they use the same
No,
chamber?
no. They, geochemically, they're independent. So they're sourced from 2 different portions of the hotspot. So they have separate magmatic systems. Yeah. What about?
Really different than Mauna Loa and Kīlauea?
Okay, the question is, what about Hualalai's source? Okay, so in Hawaiian volcanoes, in a really big perspective, we have, well, not we, but the scientists, some of them have denoted changes where certain volcanoes are called Loa volcanoes and others are called Kea volcanoes. So, Loihi, Kamakaʻehu o Kanaloa, and then Mauna Loa and Hualalai are on a Loa trend. Kīlauea, Mauna Kea, Kohala are on a Kea trend. Okay? So the hotspot is over here under Kīlauea and Mauna Loa, and when these volcanoes move off the hotspot, the periodicity and frequency of eruptions gets greater and greater. But also the degree of melting that feeds these volcanoes decreases because they're no longer close to the blowtorch, So they're on the side, so their chemical compositions actually evolve based on that. And so that chemistry, because it's a post-shield chemistry, is different from a shield chemistry. But when you look at their isotopic differences, we can fingerprint them to the Kea trend or the Loa trend. So they're genetically related, but they're not the same composition.
We've got time for one more question.
Over here.
I wanted to know what you think of the Helena slump.
That sounded like a me question. So the question was, what do I think about the Helena slump? And so one thing I will say is, so the structure that causes Kīlauea's flank to move to the south is not actually that landslide structure. So it is a low-lying fault that we call, so the phrase décollement fault is actually a generic phrase. It just means a very low angle, almost horizontal fault. But here we call it the décollement fault. And so there's this sliding surface that goes under pretty much the entire island, so under Kīlauea and then also under Mauna Loa. And essentially, as the volcano gets built up, it gets slid uphill, in fact. So the volcanic pile presses down on the old oceanic floor, and then as it builds up, it pushes things up the flexed crust. So it's slip on this structure that causes that south flank to move regularly out. In addition, there are these landslide blocks that we can see that create the Helena Poly, the Hole Poly, all the dramatic polys that we can see. Ocean seismic reflection profiles have shown that those structures don't seem to go all the way down to the décollement. So for a while, there was a question, does the Helena Poly go all the way down to the décollement? And if we saw an earthquake or one of these slow earthquakes that we used to get, could that mean that the whole slump would go? And the seismic reflection profiles showed that the slumps themselves stayed within the crust. They didn't go all the way down to the fault. So they are much shallower, and in some ways, so they're independent and kind of piggybacking on the flank. The biggest time that the polys showed motion was during the 1975 Kalapana earthquake. So they certainly are capable of moving together with a lot of shaking. So the hypothesis right now is that the poly only really gets going when there's a large enough earthquake to cause shaking. Also, because of the décollement, the hypothesis is that the action of moving the volcanic pile uphill essentially creates a backstop, which should prevent a catastrophic slump of the kind that people really worry about with the Helena slump. So not only is most of the motion we see not the slump, but in fact the faults, the presence of the faults creates this little toe at the end, which should prevent that slump from really, taking off. So that might be more than you wanted, but that's everything. Yeah. Okay. Yeah.
Answer. She had a hula that went with it. Was that awesome? That was great. So for those of you who are staying on the Kona side of the island, please drive careful on your way back. It's about 2.5 hours, and roads are, of course, very dark and windy. 2 weeks from tonight, for our local residents, we'll have a special after dark in the park on Big Island woodturners. Mark Stebbins will be here with some of their artwork, so absolutely phenomenal. Should be really nice. And I want to extend a